thanks for the introduction. So today I'll be telling you about homology, cobordism, and Heegaard Floer homology. And the work that I'm talking about today is joint with various subsets of Irvin Dye, Kristen Hendricks, Matt Stoffergen, Lin Truong, and Ian Zemke. So I'm a low-dimensional topologist, so I study 3 manifolds, 4 manifolds, knots and surfaces inside of them. So today we're going to be talking about 3 manifolds. We're going to be talking about a particular class of 3 manifolds. So we're going to be talking about homology spheres. So those are 3 manifolds that have the same integral homology as S3. So let me give you some examples of homology spheres. So the first example I'll give you of a homology sphere is S3. What's another example of a homology sphere? The Poincare homology sphere. So one way to think about the Poincare homology sphere is you can take a dodecahedron and you can identify opposite faces. You'll have to do a little bit of a click, so just sort of do the smallest twist you need to do to identify opposite faces of a dodecahedron. That's one way to describe the Poincare homology sphere. What are some other homology spheres? Well, you can take a knot in S3, and now let's remove a tubular neighborhood of that knot. So now you have a manifold whose boundary is a torus. And so now let's glue in a solid torus, but let's glue it in a different way than we cut it out, right? So when we, so originally this curve bounds a disk in S3, but now we've taken out a solid torus, and we'll reglue the solid torus so that this curve bounds a disk. And so this is called +1 surgery on this knot. The +1 refers to how we're gluing back in the solid torus. And it turns out it's an exercise using Mayer-Vier torus to check that for any knot in S3, if you sort of do this recipe, you'll get back a homology sphere. What's another class of homology spheres? Another class are the so-called Brieskorn homology spheres. Denoted sigma PQR, where P, Q, and R will be relatively pairwise relatively prime. So what do we do? So let's look at the 0 set of the polynomial x to the p plus y to the q plus z to the r equals 0 in C3. Okay, and so let's take this and let's intersect this with a small sphere centered at the origin, right? So this is 6 real dimensions. So let's intersect this with a small S5 centered at the origin. Great, so this is going to be 4 real dimensions intersected with 5 real dimensions in 6-dimensional space. So generically, that'll be 3 dimensions. And so you can show that this gives you a homology sphere, and this is what we're going to call sigma PQR. The Brieskorn homology spheres are a special family of Seifert-Fiberd spaces. So a Seifert-Fiberd space is a 3-manifold that can be written as a union of circles in a particularly nice way. And there's some overlap in between the examples that I've given you. So the Poincare homology sphere, well, this is the same thing as +1 surgery on the right-handed trefoil, and it's also the same thing as sigma 235. All right. So these are some examples of homology spheres. What are some other examples of homology spheres? Well, you can take the connected sum of any of these, and you'll still get a homology sphere. So if we look at the set of homology spheres under the operation of connected sum, we get a monoid, right? We're studying manifolds up to homomorphism. So if you connect sum with S3, well, that doesn't change your manifold. Okay, so we'll look at homology spheres under connected sum. And we get this monoid. Well, we'd really rather have a group, right? So let's mod out by some equivalence relation and get a group out. So, well, what equivalence relation should we mod out by? We're going to mod out by something called homology cobordism. So I will denote this theta 3z. 3 because we're talking about three-dimensional manifolds. Z because we're talking about integral homology. And this denotes the homology cobordism group. So now I need to tell you what this equivalence relation is. So we say that two three-manifolds Y0 and Y1 are homology cobordant, which I'll denote with a twiddle, if there exists a smooth, compact four-manifold W such that, well, it should be a cobordism from Y0 to Y1. So that means that the boundary of W is minus Y0 disjoint union Y1. So that's the first part. And then, well, the homology part says that on the level of homology, W looks like a product. So one way of saying that is that the map induced by inclusion on homology from either boundary component to the four manifold, this is an isomorphism. Great. Okay. So maybe you're wondering, well, why do we need this homology condition? Well, if we didn't have this homology condition, then any two three-manifolds would be equivalent. So that's sort of too boring. And somehow this is sort of just right. So let me give you some examples of homology cobordisms. So, wait, I said that W on the level of homology looks like a product. So, well, if I take a product, that's going to be a homology cobordism. So any three-manifold Y is homology component to itself via just the product. Implicitly I claimed that this gives us a group, so we better get inverses out of this construction. And indeed we do. So it turns out that the inverse of Y is minus Y with the opposite orientation. So in other words, that tells us that Y connects some minus Y better be homology cobordant to S3. So let me tell you what the homology cobordism is here. So you take your three-manifold, remove a ball, cross that with I. So let me draw a cartoon. So here's Y. I took out a little ball. I cross that with I. Great. OK, so then well, the boundary of that's going to be Y connects some minus Y. And then, well, if you just take out a 4-ball from that, right, you can check the boundary of this is going to be, well, Y connects to minus Y, and then from removing here, I get a boundary S3. And then again, it's an exercise to check that since Y was an integer homology sphere, this thing indeed satisfies this homology condition. Great. OK. So we really do get a group. We have inverses. So, well, now the next natural question is, what is the structure of this group? So what does this group look like? well, maybe the first thing you're wondering, well, is this thing non-trivial, right? That's sort of maybe question 0. And so indeed it is. So that was answered by Vauquelin in the 50s. So he defined a surjective homomorphism from the homology cobordism group to Z mod 2Z. So Y gets sent to 1/8 the signature of W, where W is a smooth, compact spin 4 manifold, simply connected, whose boundary is Y. Wait, so the fact that this is a surjective homomorphism implies that the homology cobordism group is non-trivial. All right, so I wasn't alive then, but what I've heard is that it was a reasonable conjecture at the time that this is actually an isomorphism. But as we'll see, that's actually far from true. So what did we learn next about the homology cobordism group? Well, in the 80s, Finterschel and Stern showed that, in fact, the homology cobordism group is infinite. They showed that they found an element of infinite order in the homology cobordism group. And then a few years later, Furuta and independently Finterschel Stern showed that they showed an infinite rank subgroup in the homology cobordism group. And then a few years later, Afroshev proved that there's a direct summand in the homology cobordism group isomorphic to the integers. So maybe one remark, right? So having a Z summand is a stronger statement than having a Z subgroup. So for example, the integers are a subgroup of the rationals, but the rationals don't split as Z direct sum some other group. So these results were all proved using gauge theory. And maybe one other result I want to mention is due to Manilescu from 2016. So what did he prove? So he proved that if the Rocklin invariant of Y is 1, then Y is not order 2 in the homology cobordism group. Great. Okay. So this result sounds sort of technical. You might wonder why am I highlighting this? Well, it turns out due to earlier work of Galuski, Stern, and Matsumoto, this is from the late 70s or early 80s. Turns out that this implies that it gives a disproof of the high-dimensional triangulation conjecture. So it implies that there exists topological manifolds in every dimension 5 or greater that are not triangulable. All right. And so the first result that I want to tell you about today is about the structure of the homology cobordism group. And this result is joint with Irvin Dai, Matt Stoffingen, and Lin Chuang. Great, so we proved that the homology cobordism group has a direct summand isomorphic to z to the infinity. And I can even tell you what this is generated by. This is generated by a family of Seifert fibers of Rees-Cohen homology spheres. This is generated by sigma 2i plus 1, 4i plus 1, 4i plus 3 for any positive integer I. And this is the strongest result to date about the structure of the homology cobordism group. So in particular, it's still open whether there's any torsion in the homology cobordism group. All right. What other questions might you ask about the homology cobordism group? Well, you might ask about what types of manifolds can represent a given class in the homology cobordism group. So the next question I want to address is what types of manifolds can represent a given class in theta 3z. So let me give you some results, sort of affirmative results. So in the early 80s, Chuck Livingston showed that every homology sphere is homology cobordant to an irreducible three-manifold. So for homology spheres, being irreducible is the same as saying that you can't be written as a non-trivial connected sum. And a few years later, this result was improved to show that every homology sphere is homology cobordant to a hyperbolic manifold. So you can think about this as saying sort of like hyperbolic manifolds are sufficiently generic. And this result is due to Myers. Okay, so in light of these results, well, you might ask, well, what other families of manifolds are or are not sufficient to such that any three manifold is homology cobordant to that type of manifold? So the first result, sort of interesting result in that direction, was in 2017. So on the other hand, there exist homology spheres that are not homology cobordant. To any Seifert fibered space. So this is proved independently by Froishov, Francesco Lin, and Matt Stoffingen. Great, and so what's an example of a homology sphere that's not homology cobordant to a Seifert fibered space? Well, it turns out, so for example, if I take sigma 237, remember these are the Rees-Cohen homology spheres, connect some with itself. If I look at this class in the homology cobordism group, well, this is not represented by any Seifert fibered space. So it's represented by any Seifert fibered space. However, well, what do you notice? Well, well, it's a connected sum of Seifert fibered spaces, right? So, well, in particular, it's homology cobordism to a connected sum of Seifert fibered spaces. So, in light of this, well, the next natural question to ask is, well, do Seifert fibered spaces generate the homology cobordism group? So, in other words, is every homology sphere homology cobordism to a linear combination of Seifert fibered spaces? So that's the second result that I want to tell you about today. So the theorem, which is joint with Kristen Hendricks, Matt Stoffagen, and Ian Zemke, is that Seifert fibered spaces do not generate the homology cobordism group. In fact, they really don't generate the homology cobordism group. So what do we mean by that? Well, let's consider the subgroup generated by Seifert fibered spaces. So let's let theta SF denote the subgroup of the homology cobordism group generated by Seifert fibered spaces. Great. Okay, and so the fact that Seifert fibered spaces don't generate the homology cobordism group means that this group is not the whole thing. So the quotient, so in particular, if we look at the quotient of the homology cobordism by this subgroup, that measures the failure of Seifert fibered spaces to generate the homology cobordism group. And so if we want to prove that Seifert fibered spaces really don't generate the homology cobordism group, well, what we prove is that this quotient is really non-trivial. This quotient is infinitely generated. And so, well, we prove that the family Yn, so Yn is going to be plus one surgery on some knot. So right, T23 that's the trefoil knot. And then connects some with minus 2 copies of the torus knot T2n, 2n plus 1, and then connects some with the torus knot T2n, 4n plus 1. Let's say n is at least 3 and n is odd. So this family is linearly independent in that quotient. So this family Yn is linearly independent. In this quotient. All right, so those are the two main results I wanted to tell you about today, that the homology cobordism group has this Z infinity direct summand, and that it's not generated by Seifert fibered spaces. And so I want to spend the rest of my time today telling you about how we prove these results. So both proofs rely on Heegaard Floer homology. So the proofs, they rely on a particular refinement of Heegaard Floer homology called involutive Heegaard Floer homology. So Heegaard Floer homology is a package of invariants for 3 manifolds, 4 manifolds, and knots inside of them, defined by Ajroff and Szabo about 20 years ago. And then this involutive, it's some extra structure on these invariants that was defined by Kristen Hendricks and Chip V. Manilescu maybe about 5 to 7 years ago. So for the purposes of today, I'll mostly be black boxing these invariants, but I want to tell you sort of what formal structure they take on. So to a 3-manifold, well, the Heegaard Floer homology machine associates a chain complex. So to a 3-manifold Y, we get a chain complex. So what kind of structure does this have? This is a chain complex over a polynomial ring. And then plus it has some extra structure. So we get some extra structure from Hendricks and Manilescu. If you're curious, this extra structure is a homotopy involution on the chain complex. Right, so it's a chain map that squares to be homotopic to the identity. Where does this chain complex come from? So you describe your 3-manifold via a Heegaard diagram. And then from that Heegaard diagram, you build a symplectic manifold, and you do Floer homology on that. And then you get out a chain complex that depends on your choice of Heegaard diagram, but up to chain homotopy equivalence, it's independent of any choices you might have made in the construction. All right. So our goal is to understand 3-manifolds up to homology cobordism. So we want to see how homology cobordism is reflected in these invariants. Let me tell you some useful properties of these invariants. So if I reverse the orientation on my manifold, well, you'd hope that the chain complex that gets associated to that is somehow related to the one associated to Y, and it is. You just dualize. So just dualize over the ground ring. Similarly, well, if I take the connected sum of two 3-manifolds, you'd hope that the chain complex associated to those is somehow, again, related to the chain complexes associated to Y1 and Y2, and that's indeed true. It's just the tensor product of those two chain complexes. And then lastly, well, if you have two 3-manifolds that are homology cobordant, you'd hope that their chain complexes are somehow related in a nice way, and they are. Their chain complexes are what's called locally equivalent. So this is some equivalence relation on chain complexes. It's weaker than chain homotopy equivalence. I'll denote this with a twiddle. Okay. So I want you to sort of stare at these properties for a minute and think about sort of what's the natural thing that you could do, right? Our goal is to understand the homology cobordism group, and somehow maybe we can push that into a more algebraic question about understanding chain complexes up to some equivalence relation. Right? So remember, to build the homology cobordism group, we looked at homology spheres up to homology cobordism under the operation of connected sum. So here, well, we can let's look at chain complexes. Let's say certain chain complexes. Basically, ones that look like they could have come from this machine. Okay. Well, if you look at chain complexes with some extra structure that, don't worry about the extra structure too much. Well, chain complexes under tensor product, right? This forms a monoid. And now, well, we have this equivalence relation. So let's look at chain complexes up to this equivalence relation under tensor product. And it turns out that this forms a group. So I'll denote this with a fancy I. Right? And sort of sort of by construction, well, we get a homomorphism from the homology cobordism group to this more algebraically defined group, right? So we'll just send the class of a three manifold to the equivalence class of its chain complex. So that sounds great. Maybe the bad news is that this group isn't actually that easy to understand. So we just sort of took one hard problem and made it into a different hard problem. But fortunately, there's a homomorphism from I to a group that we that we do understand better. So Irving, Matt, Lynn, and I prove the following proposition. So there exists a homomorphism. This homomorphism, it's almost surjective. So we get a homomorphism from this hard-to-understand group I to this nicer group I hat. And, well, as a set, I can tell you exactly what I hat is. So where elements in I hat are parametrized by sequences. So what kinds of sequences? Sequences of, well, certain sequences of integers. So they're parametrized by sequences AI, BI, where the AIs take values in the set plus or minus 1, and the BIs are non-zero integers. Great. Okay. So instead of studying this group I, we're going to take this homomorphism to this group I hat, where I hat, as a set, we understand it. Well, a group is a set together with a binary operation, so maybe you're wondering what the operation looks like here. So let me give you some examples. Right, so elements in I are equivalence classes of chain complexes. Similarly, elements in I hat are equivalence classes of chain complexes. And so these sequences somehow, given a sequence, there's a way to sort of convert it into some kind of standard chain complex. And then I can take the tensor product of those chain complexes, and it won't be in that nice standard form, but then I can sort of massage it so it is. So that's how I'm getting these calculations. So in I hat, well, if I take the sequence negative 1, 2, this is an abelian group, so I'll denote the operation with addition, plus negative 1, 1. Well, this gives me negative 1, 2, negative 1, 1. So this maybe makes you think that maybe this operation in this group I hat is straightforward. Let me give you one more example. So if I just change the sign on one of these, so plus 1, 2, plus 1, 1, it turns out that the sum of these gives you plus 1, 1, plus 1, minus 1, 2, plus 1, 1. So maybe this example makes you think maybe this operation isn't so easy to understand. Great. Okay, but so our goal is to try to use this group to understand the homology cobordism group. So what have we done so far, right? So we have the homology cobordism group. We have this map to this group I that was sort of hard to understand, but then we have this map to this group I hat, where elements in here are sequences. So we have a recipe for taking a three manifold and getting out some sequence. So let me give you some examples here. So let me give you some families of examples. So let's let the manifold Zj be the Brice-Korn homology sphere sigma 2j plus 1, 4j plus 1, 4j plus 3. Wait, let's say j is at least 3 and odd. Great. Well, then the sequence that's associated to this 3 manifold via this homomorphism, so h hat of Zj, this is just minus 1j. Let me give you a couple more examples. So the next example will be these manifolds Yn, which will be plus 1 surgery on T23 connects some minus 2 T2n 2n plus 1 connects some T2n 4n plus 1. Oh, actually, sorry, this is, we don't need this. J here can be maybe any integer, sorry. Here, this is where we want n to be at least 3 and n odd. All right, so what sequence gets associated to this 3 manifold? The sequence that gets associated to Yn is plus 1, minus 1, plus 1, minus n plus 1. And let me give you one more example. Let's look at Yn connects some Yn, where let's say n is greater than or equal to n. The sequence that gets associated to this is you basically just like concatenate the sequences associated to each of these pieces. So it's plus 1, minus 1, plus 1, minus n plus 1, plus 1, minus 1, plus 1, minus m plus 1. Great. Okay. And so why are these examples particularly useful for us? Well, maybe these manifolds look familiar, right? These are the manifolds that showed up in Theorem 2, which said that the homology cobordism group is not generated by Seifert fibered spaces. And these are the manifolds that show up in Theorem 1, saying that the homology cobordism group contains a Z infinity direct summand. So here's a proposition due to Irving Dai, Matt Stoffagen, Lin Chong, and myself. So for each non-zero integer, we get a homomorphism from this group I hat to Z. Right, so elements in I hat are parameterized by these sequences. What does phi k do? Phi k is just a signed count of how many times k appears here. So this is equal to the number of bi's, where bi is equal to k, minus the number of bi's, where bi is equal to minus k. And so what's the result? The result is that this is a homomorphism for each k. So this is a homomorphism. Right, so earlier I gave you these examples of addition in this group I hat where it looked kind of chaotic, but this result's telling you, well, okay, it can be a little chaotic, but in a sort of controlled way, right? So for example, if you look back at the example that I erased, it satisfies like the sign count of the ones. So if you got a +1, you got a -1 that canceled it out. So it all balanced. Great. All right, so with these homomorphisms, well, let's look at these examples here, right? So, well, looking at these examples right here, you get the following corollary. So you get the corollary, which is that, well, just take the direct sum over k of these bk's, right? So, well, right, you start with the homology cobordism group, well, then you map it to this group I hat, and then you map it to z to the infinity, right? Well, this is surjective, right? Because if you look at these examples here, right, this tells us that phi k of zj is just delta jk, right? Because remember, phi k is a sign count of how many times k appears in this sequence. So great. And so, well, that tells you that this family of manifolds gives you a surjective homomorphism from the homology cobordism group to z to the infinity. Well, z to the infinity is free, so it necessarily splits. So that gives us the direct summand. So that's the proof of theorem 1. And now for the proof of theorem 2, which was that Seifert fibered spaces don't generate the homology cobordism group. Well, that's where we need this family of examples. So what you would hope for is that for anything in the span of Seifert fibered spaces, you'd hope that the sequence associated to those manifolds takes on some particularly nice form. And indeed it does. So we have the following proposition, which says that, well, if I have a sequence that's in the image of the subgroup spanned by Seifert fibered spaces, well, then that sequence has to have a particular form. The absolute values of the BIs has to be non-increasing. Great. So you look at this, and that's where this family of examples comes into play, right? So remember the BIs, those are here and here, and you say, oh, well, yeah, the absolute value increases here, so this manifold's not in the span of Seifert fibered spaces. And then with a little more work, you can look at linear combinations of these. So I gave you one example here. And again, if you look at the absolute value of the BIs, they also violate those inequalities. So those are the proofs of the two theorems, and that's what I wanted to tell you about today. Thanks for your time.